So now I'll just show you some results from our diesel-like simulation. So at Sandia National Lab, they had done, very extensive experimental work. Okay. So this is a constant volume reactor. Okay, this is schematically it is shown the reactor. Okay. So around the world, several people use these kind of reactors, okay, to create diesel type conditions. Okay. In diesel engine, it's a lot more complicated, and also you cannot really make a lot of measurements. Okay. So to take care of that, they do these constant volume reactors, which has a lot of windows, and you can put a lot of measurement capabilities, okay, more detailed laser based measurements. So what you do is you burn a mixture, it could be natural gas or something, okay, to create that high temperature, high pressure condition. Okay. And then you can control the environment. You can also put CO2, H2O, okay, to simulate the diesel engine condition. Okay. And then you inject your fuel, whatever fuel, like diesel fuel or gasoline fuel, whatever fuel, or heptane. Okay. And then you make measurements. So they have produced a lot of experimental data, which is available online. Okay. You can go to the site to see a lot of data. Okay. And it's very well organized if you download the data. Okay. So now, a lot of people around the world, they are also doing computations in this constant volume reactor. Okay. So then, of course, you do 3D computations. Okay. So we have done some for the spray flames. So I'll just show you some results. So for computational work, we use this software Converge, which is a 3D diesel engine software. So we are simulating again this constant volume reactor. Okay. These are just some features of the software. Okay. One very attractive feature is this: it has this adaptive mesh refinement. So during your computations, the mesh is continuously refined. And then you can use detailed chemistry through this Sage solver. So you can download like the chemistry thermo files and use them directly. Oops, did I miss something? So okay, so those are the same details. So then for our computation, first we did some validation study. Okay. So here these dots are the experimental data. Okay. So what is the configuration now? So you have the initial hot temperature environment. Okay. Pressure is about 50 atmosphere. It's a high pressure condition. And then you inject, in this case, heptane spray. Okay. And then this is the liquid penetration, how the spray penetrates, okay, in that reactor. So penetration plotted versus time. Okay. So this is the experimental data, and then it's showing the effect of mesh refinement. So 0.5, 0.25, 0.125. Okay. So as you go to 0.25 and 0.125, you get almost grid independent results. Only thing is the initial part is not well reproduced by the CFD work. Okay. But then it gives a good liquid length. So main idea was to show the effect of grid, or show the grid independence. So most of the results then we got for 0.125 millimeter. So this shows the okay, transient process. Okay. So this is the spray, okay, and what is plotted is the local equivalence ratio. So like inside it is 2, 1, okay, then outside is lean. So this is at, you can see 0.0003 seconds starting from 0, okay, and then at 0.7 millisecond, okay. Oh, sorry, here we should go here first. So at 0.5 millisecond, okay, the spray gets ignited. Okay. And ignition now occurs in a rich mixture. Okay. Equivalence ratio there is about 2. Okay. And then from ignition, then a flame is formed in the spray. Okay. And of course, then this flame expands as you inject more fuel. Okay. So this is at 0.1, okay, or 1 millisecond. So this calculation is over 1 millisecond, because there are a lot of steps though. Okay. So basically, these are the temperature contours and then equivalence ratio contours. So temperature contours are shown, with the colors, where the equivalence ratio. This is like the theoretical equivalence ratio. Okay. Obviously, combustion has occurred, so there is no like fuel and air as to calculate the equivalence ratio. Okay. So there is a you can calculate the equivalence ratio based on your number of carbon atoms, number of hydrogen atoms. Okay. So it's the theoretical equivalence ratio at those locations. So like the equivalence ratio before combustion, you can say. Okay. Okay. This shows the time evolution of the same thing over very short time, 1.5 seconds. So I can show that again. Oops. So the injector is located right here. Okay. So this is a cube. Only some of the dimensions are shown. It's actually a cube. So you're showing the results right into the center of that cube, okay, which is like a symmetric plane. Okay. Now some emissions. Oh, before emission. Okay. Now, since we are using a detailed chemistry model, okay, or I should say like semi-detailed chemistry model, you can look at different species, okay, and you can identify the flame structure in even this complicated flames. So if you plot C2H2 contours, okay, that indicates the rich premixed zone, because C2H2 we know from our counterflow calculation is produced in the rich premixed zone. Okay. Remember earlier I was showing you today the counterflow results. So even for this turbulent spray, very complicated flames, okay, the fundamental concepts, okay, hold, right. So this is the overall flame. Rich premixed flame is here, then here the diffusion flame. Okay. So C2H2 is produced in the rich premixed flame. OH is a good signature for the diffusion flame. Okay. So that shows the location of the diffusion or the non-premixed flame. Okay. And inside you have the rich premixed flame. Okay. So this is the NO distribution. Okay. So you can see that lot of NO is produced in the where? In the diffusion flame. Okay. Some also produced in the rich premixed flame. Okay. So the counterflow simulation help us to do these kind of things. And then if you look at a pH aromatic species like C6H6, This is produced again in the inside the rich premixed zone. So, premixed combustion produces the soot. Okay, this is a precursor for soot. Any questions? Okay. The flow is of course very transient. It's turbulent obviously. Now we did more detailed analysis for the same flame. So this is that model of the diesel combustion showing there. So again, the NO distribution. So this is the total NO. But now here we did not do like remove the reactions and do calculation, because each calculation takes like about 3 days. Okay, it was difficult to do. So, but we can plot the individual species. Okay, so that tells us a lot about individual sources of NO. Okay, so like NO2. Okay, so that also means that the NO2 is produced outside. When you produce NO, then NO forms NO2. Okay. Okay. Now this species SCN is involved in the production of. Remember which NO? Prompt. Okay. So again, it indicates that the prompt is formed. Okay, in the rich premixed zone. Okay. NH also more or less there. Okay. So this is like between the rich premix, a little bit outside the rich premix zone. Okay. N2O mechanism, okay, is outside the non-premixed zone. Okay. So it's kind of in the lean zone. Okay. NNNH is like basically in the rich premix and some in the diffusion flame zone. Okay. So it tells us about the individual contributions. So this was a very interesting way of looking at the different zones. So again, we did both heptane and heptene. Okay. So you see this so what is plotted here? So you have lot of points in space, right? You have X, Y, Z. Okay. I don't remember number of grid points. Okay. There are like millions grid points or more. Okay. So if you plot all those points, you can plot in a different coordinate system. So along the x-axis you have the temperature, and along y-axis you have the equivalence ratio. Again, this is the equivalence ratio corresponding to the non-reacting case. Okay, we can extract, looking at the atomic species. Okay. So it gives very interesting results, lot of insight. So look at the thermal NO. Okay. So this is the non-premixed zone, because the temperature is the highest and equivalence ratio is about 1. That's where the diffusion flames are. Equivalence ratio close to 1 and the high temperatures. And then here, if you look at SCN, okay, so SCN is in the rich premixed zone, because what is the equivalence ratio? Like 4. And temperatures are lower, maybe like 2000. Okay. And again, it shows that the heptene, it produces more SCN. Okay, so it will produce more prompt NO. Okay. We did not do directly the prompt NO, but from SCN we get quite clear evidence. Then N2O mechanism, it also produces an NO. So N2O species is also higher, okay, in 1-heptene. And where it is produced? Okay, very lean and low temperatures. So this is a very unique way of looking at the details of the flame. because if you do just contours, it's very difficult to make a lot of conclusions. And what is this one now? NNH. Okay. So NNH is produced more in the rich zone and relatively higher temperature, but there is more NNH also in 1-heptene compared to heptane. So all NO formation routes are more pronounced in 1-heptene flame. Yeah, I still haven't found the reason why this slide jump. And it skips to 3 slides suddenly. Okay, so that was the session on NO. Okay, and the rest of the slides are on Soot. By the way, when I send the material, I had only like 15 slides on these two sessions. Okay, so then I realized 15 slides is not enough for 2 sessions. Okay, so last evening I added another 20 slides, from my previous papers or other sources. So now there are like so if anybody wants, just ask Professor Day, maybe they can send you in a different format, because I think you already got the pen drive, right? Yeah. Okay, now this is the overall information of how the soot formation occurs in flames. Okay. So these are the major steps, the first bullet. Okay. So first you form some gaseous species. So the fuel chemistry is important there. What are the precursor species? Like acetylene, benzene, and also like other PAS species. Okay, like pyrene, you form those species. Okay. So from benzene, you make larger molecules. Okay. And these are aromatic molecules. Okay. So you go to pyrene, but those are 4 rings. Okay, and then larger ones. Okay. So the chemistry of forming these larger molecules is not very well understood. Then from those larger molecules, the next process is the particle nucleation. You form particles, so you go form solid particles. So that process is probably the least understood. How do you form the solid particles? Okay. So that's particle nucleation, and then there is a growth of this. These are very, very small particles, and their surface area it grows. So it grows due to agglomeration, that they particles they combine together, and also there is a surface chemistry involved. Some species get deposited on the surface. So the surface grows. Okay. So the surface growth is the third process through chemical reactions and agglomeration. And the fourth major step is the oxidation of the soot. Okay. So now the models are appearing. People are starting reporting the models which can model these all these processes. So these are some of the details of the first bullet. So as fuel decomposition occurs, intermediate hydrocarbon species are formed in the fuel rich region. Okay. Which undergo further reactions to form C2H2, I should write in that order, C2H2, PS species. So C2H2 are considered the major precursors. Okay, that's the, you can say, state of the art. Okay. And then nucleation, through nucleation and polymerization, it forms primary particles, and then the surface grows through surface reactions with coagulation, and then also oxidation. Yeah. polyatomic aromatic hydrocarbons. Okay. Right? Polycyclic, yeah. Polycyclic, you are correct. Polycyclic.
Most of the aromatics are cyclic.
Yeah. And you know why they are called aromatic? Because of the smell. You know, some people don't know. Okay. You know, I used to think of this like some kind of a chemistry name, aromatic. It's because of the smell. Okay, yeah, polycyclic. Okay. Where were we? Here. So now the kinetic model, the reaction mechanisms, okay, what like I am aware of. So they have the capability to for the formation of up to pi ring, which is a 4-ring structure. Okay, benzene is 1 ring, you know, 6 carbons. Okay, so CH, CS, CS, so 6 C6H6 is benzene, and then you know from there you can form pyrene. Okay. These are more details of the surface growth. Okay, and then some of the soot is oxidized. Now, for engineering applications, this is an important property for different fuels. What is the smoke point? Okay. So this is defined for a given fuel, that the fuel's propensity to form soot. Okay. So you keep increasing the fuel flow rate until you see the soot. Okay. So this is reported in terms of the flow rate. Okay. So for acetylene flame, okay, it's so it's like an index. Okay. It's 0.51 compared to this flame. I don't know if what is this C6H70. I think I don't know how to check this. Okay. But anyway, the main point is C2H2 propensity is much higher, because at very low flow rates it will form soot. Okay. Okay, this is graph is from Turn's book, so shows sooting flames and non-sooting flames. Okay. So it's a diffusion flame. What is plotted is the soot volume fraction. Okay. So this I think is a jet flame. So along the center of the flame, okay, height from the burner, distance from the burner. Okay. So it's non-dimensionalized, because what will be X stoichiometric? That will be like the flame tip. Okay. So 1 will be the flame tip. So anyway, what is shown? So 1 will be the flame tip. So flame will be here somewhere. Tip will be here. Then you go further. Okay. So the soot volume fraction. Okay, what is soot volume fraction? It's a fraction, and it's volume fraction. So that kind of tells you. So is the volume occupied by the soot particles per unit gas volume. Okay. So if you take, okay, if you calculate the volume occupied by all the soot particles, divide by the gas volume, that gives you the volume fraction. So this is, there are 3 properties. There are slides further. This is one of the important soot volume fraction. Okay. And the value is 10 to the power 6. Okay. Minus 6 rather, I should say. It's not 10 to the power 6. Okay. Those are the units. So whatever value you take, like let's say here the value is 5. So 5 times 10 to the power minus 6. This is equal to 5. Okay. So that's how you read this graph. So anyway, so if you look at, okay, for example, butane, for one condition it is non-sooting. So, the soot is produced, okay, and as now you go toward the tip of the flame, it gets oxidized. Okay. So, the soot volume fraction increases and then decreases. But if it is a sooting flame, then all of the soot is not oxidized, some escapes the flame. So, that is a sooting flame. So, you will see the yellow zone, where the soot is produced. Okay. Same thing for this propylene. Okay, now I don't remember that what are the if you can go to this paper. Okay, so you want to see the more details. Yeah, this one is there in your notes. This figure. So same thing happens here. So propylene for this condition becomes sooting flame. Okay. Yeah, this is the paper Combustion and Flame 1986. By the way, like you can easily see soot, okay, you have this burner in your house, whatever stove. Okay. So you just put the spoon on the stove. Okay. Within like a second, you'll see that carbon, that's black deposit. Okay. Because when you put the spoon, what happens is the flame gets extinguished at the spoon. So there is intermediate hydrocarbons are produced, and it produces soot. So you can see the soot right away. Okay. From the incomplete combustion. Now I'll show some results. Okay. First for the counterflow calculation, and then for the the Sandia reactor calculation. So here the student was doing this partially premixed flame with two reaction zones. Okay. So you have you control the phi value in the fuel jet, and this is air, and then you get two flames. Okay. So you can control the equivalence ratio. Now here to show the results, this is the equivalence ratio. So these are the cases student did. So this will be the diffusion flame. So these are the partially premixed flames. Okay. Now when you plot the results, it is very difficult to plot along the x axis, from 2 to infinity. That's a very wide range. Okay. So we just used, instead of this phi, we use this variable. Phi is this big phi is 1 minus 1 over phi. So when it is equivalence ratio is infinity, diffusion flame, this will be 1. Okay. If you go to premixed flame, what will be phi? This will be 1, right? So then this will become 1. So when you going this way, oh, 0, sorry, 0. Okay. So for premixed flame, this big phi is 0, but diffusion rate is 1. So it varies between 0 and 1. Whereas for phi will vary from 1 to infinity. Okay. So you control the equivalence ratio. In this counterflow, you also control the residence time by controlling the strain rate. Okay. So if you decrease the strain rate, you are increasing the residence time, then more soot will be formed. Okay. So you can check that, you can see that effect also. So there are a lot of information here. Okay. But let's see if I can. So this is the fuel side, fuel jet side. This is the air side.
Sir, with increasing the reagent time, how more soot will be found?
Increasing what?
Reagent time.
No, decreasing the resistance. Decreasing, yeah. Okay. You increase the strain rate, it decreases the residence time. Okay. Yeah, so you decrease the strain rate to see more soot. Okay, so then stagnation plane is here at 0.75 something. Okay, this is shown by the broken line or other way around. Yeah, by the broken line is the NPZ, the non-premixed. NPZ is the non-premixed flame. This is the rich premixed flame. Okay. So once you see that, and then blue line is the heat release rate. Okay. So that also shows the location of the flames. Actually, that's the best way to look at the location of the flame, heat release rate. So a lot of heat is released, produced in the rich premix flame, and then in the non-premix flame. Okay.
Sir, one doubt.
Yeah.
In the case of methane combustion, whether the precursor acetylene can form
Acetylene is formed in the rich zone.
for
But-
methane
Yeah.
because there it's only CH4,
No, some acetylene is formed, okay,
it becomes C2.
because of C2H6. Yeah. But for methane, most of the case the prompt NO or the thermal NO, and very little soot. Okay, methane flames, because it doesn't form much, benzene. Yeah.
Higher the number of carbon atoms.
Yeah, as you increase the number of carbon atom, yeah, sure, correct. Yeah, more soot will be formed. Yeah. Not just carbon atom, also the ratio carbon to hydrogen. Okay. So if you increase that ratio, more soot is formed because there is more carbon compared to hydrogen. Okay, so heat release rate, okay, and this green is the temperature. So you see the highest temperature in the non-premix flame, then of course in premix also temperature is relatively high. What else? The red is the velocity distribution. Okay. Finally, this is the C2H2. So you see C2H2 peak is also in the rich premix flame. Okay. So same flame is shown here for different properties. Okay. Again, this is a rich premix flame location, non-premix. So most of the soot, formation, oxidation, everything occurs between the rich premix and the non-premixed. So that was a very interesting result. Okay. So before soot, so this is the pyrene. Okay. So pyrene is formed in the rich premix zone. Okay. And after the pyrene is formed, nucleation occurs. Okay. So then we have three properties of the soot. These are the particle number density, number of soot particles per unit volume. Okay. In this model, we also have the particle size. So particle size, the peak value is like 7-8 microns. Okay, 7-8. Not microns, nanometers. Sorry, the very small particles are found in this. Okay. So you have three properties: number density, diameter. So we assume these are like spherical particles in the model. Okay, and the soot volume fraction, which is this line. Okay. So you saw before, the very typical behavior. Soot volume fraction increases as the particles are formed, and then the surface growth occurs. And then, what is this process where it decreases? That is due to, sorry, this decrease. Sorry? Yeah, oxidation. It's very similar to, this plot, right? Oxidation. Okay. So production and then oxidation. And other things also decrease. Okay. So for soot formation, the region soot formation zone, is between the rich premix and the non-premix. Okay. And what we discussed there, that in that zone, like here, the velocities are very low. So there is a lot of residence time for the soot to form between that zone. Okay. So similar result when you increase the equivalence ratio to 8, but now a lot more soot is formed, because if you just look at the soot volume fraction, okay, it is very small actually, 10 to the power minus 14. Okay. When you go to equivalence ratio 8, what is the value? No, it's 10 to the power minus 7. So increases by a factor of 10 to the power 6. So this will be a lot more sooting flame.
Capital fee,
Sorry?
capital fee.
No, this is small phi. That's the equivalence ratio. Okay. Capital phi only goes between 0 and 1. Okay. You know, we use capital phi when we plot things versus, equivalence ratio as a function of equivalence ratio. I think there are 1 or 2 slides with that. Yeah, this for example.
You can also take log function in that case.
Pardon?
You can also take, can we take log function also?
Yeah, you could have taken your log, okay, function also. But this is becoming like a common practice to use this variable for partially premixed flames. I don't know whether we started it or somebody started it, but we use this a lot. So here we plot, okay, this is a common property which is plotted, emission index for, of, pollutants. So for example, what is emission index of NO? In the entire computational domain, you integrate the reaction rate of NO, okay, and then you divide by the fuel consumption rate. Okay. So this gives you an index for the total emission. Okay. Same way we can do for benzene, because benzene is a good precursor for soot. So there are two takeaway here. One is that the heptene flame produces more NO and also more soot. Okay. And the soot emission index keeps increasing with when you go to diffusion flames. So here phi is about 8. Here it values are shown here. So limiting case will be 1 here. That's the diffusion flame. Okay. So as you go towards the diffusion flames, more soot is produced. Okay. So as you increase the equivalence ratio, more soot is produced. But NOx is reduced. Okay. These are some details. Yeah, I will skip this, then because student was doing his PhD work, so he looked. Also, Chemkin has this capability. You can look at the reaction path analysis. So you can look at the individual species. You can choose one, let's say acetylene, and then see, okay, where is this acetylene? What are the important steps to go from fuel to acetylene? Okay, or you can choose CO. So you can choose any species, and then you can do this path analysis. So here student did it for benzene. So I will not go through these details. I don't even remember at this time. But I highlighted the important observation. If you compare heptane and heptene, when you have a double bond, then there are different paths for the benzene formation. Overall result is there is more benzene formed with heptene. Okay. And the main species are 2. This is called propargyl, written here, C3H3. Okay. So you see there are 3 carbons, right? and there is a triple bond here, C3H3. So propargyl, and then this is called 1,3-butadiene, because double bond at 1 and then at 3. There are 4 carbons. So these are the 2 major species which form benzene. Okay. And for heptene, these 2 species are found more. There are more of these 2 species. So that's why it forms more benzene. Okay. So doing this, we can identify which are the paths and what are the major species. So this is well known that a lot of benzene comes from the C3H3, because C3H3 combines with C3H3 to form C6H6. Okay. Other one is the 1,3-butadiene. And then we can plot the species, like for example this butadiene. Okay. So you can see this black line is in heptane and this green one is in the heptene. So a lot more butadiene. Okay. So again, providing the evidence, okay, that's why there is more benzene in heptene flames. These are, I like these pictures of this jet flames. Okay. So this is from some earlier work. So again, you can see that as you increase phi value in jet flames, they become more sooty, lot more soot, and the flame height is increasing. Okay. So I have like just few more results. Let's see if we have enough time. So now the same, the constant volume reactor. You remember this? So same calculation we also did for soot properties. So I'll just show some flame structures which focus on the soot properties. Okay. So this one we already discussed. C2H2 is a precursor for soot and NOx. So this is formed more for the soot. So this is formed in the rich premixed zone. Okay. This is, I think, OH. Yeah, OH. So this is in the diffusion flame. Okay. This is the NO distribution again, which we already discussed. And this is benzene. PA species mainly, it's benzene. So this is formed like inside the rich premixed zone, okay, which we also saw in simple counterflow flames. Okay. A little more analysis. So this is the benzene in heptene flame, and this is in heptane. You can see there is a lot more benzene, okay, in the heptene flame. Otherwise, the conditions were identical. That is the benzene molecule. Okay. So from benzene, you can see then overall, this is the total benzene mass in that reactor. So it is plotted versus time. Okay. So that's where it starts forming. So what is the takeaway? That more benzene in heptene flame. Okay. And then there is more pyrene. So this is the 4-ring. Okay. pH. So more. Okay. Again, more pyrene in heptene flame compared to that, there is more soot. So in this, 3D simulations, we didn't have the soot model, okay, but we had up to pyrene. So this gives a clear indication for. I think now they may even have the soot model. Any questions? This, I think, is the last slide on this session. So I just added it. This is a very recent paper. The student, this was an interesting project on biodiesel. Okay. So this is a collaboration. There's Professor Dr. Avinash Agarwal. So he was making these biodiesel fuels here. Okay. And he shipped those biodiesel fuel to Argonne National Lab in Chicago. Okay. The shipping was also a very complicated process. Okay, and expensive. And also because in US there are a lot of regulations when you're shipping these fuels. Okay. So anyway, it took a long time to get those fuels. Okay. Like almost a year. Okay. And this is very interesting because in 1 year, okay, the biodiesel properties change. So he sent, Dr. Agarwal sent us the properties, what is the composition, everything, right? Okay. So then, Argonne has to send it to, the University of Illinois, Urbana-Champaign. They have the facility for this analysis because they have some biodiesel center. So the Argonne person, people, they sent it to, for again, analyzing it again. Okay. Some of the properties were similar, but there were some differences in the properties. Okay. So anyway, then this graduate student, my graduate student did the experiments at Argonne. So these are only experimental results. Okay. So they were going to write another paper, just effect of this storage, how the properties change, and how then the combustion processes, combustion behavior will change. But that paper is not out. But this paper came out. This work was done in 2015-16. It's in this journal, ASME journal. So there are many authors here, student and myself, Avinash Agarwal, then Argonne, one person, Doug Longman. So anyway, just overall results. So this is a typical, so this is in a diesel engine. So this is a typical heat release rate profile in a diesel engine combustion. Okay. Here the injection was started at -5 degree before the top dead center, or 5 degree before the top dead center. So it says -5 after the top dead center. So it's so 5 degree before top TDC. Okay. So this heat release is shown for, okay, for diesel, and then J100 is the Jatropha based biodiesel. This is the Carenza based. Okay, so there were two different biodiesel. Okay. So what you notice is, because the cetane number of biodiesel is higher, okay, ignition occurs earlier. Okay. So ignition occurs earlier, okay, whereas for diesel, you see the ignition occurs getting later. So because of this change, difference in the ignition delay, what happens is the premix, the equivalence ratio for the premix, okay, combustion, instead of, let's say, from phi 4, it will become phi 2. There will be more mixing because of that, right? Because ignition occurs later. Okay. So more heat release occurs in the premix combustion in a diesel because ignition delay is longer. So that's what you see here. So this peak, first peak is the premix combustion, and then more heat release keeps going due to diffusion combustion. Okay. So that occurs over a long period. Premix combustion is very fast, and that's where soot will be produced. Okay. So just from this diagram, we can infer, some very useful information about, what is the effect of adding biodiesel. Ignition occurs earlier, so that affects, the soot properties. Okay. Now this was, lot of effort. So these are not direct soot to volume fraction measurements. Okay. So they have this facility at Argonne. They have this video scope fitted in the engine. Okay. I don't remember the details. You can see in the paper. So they can get of the combustion process. Okay. And so then those are related to temperature, and through that there is a software which relates and predicts the soot volume fraction. So these are not very quantitative, but qualitatively it can see the effect. Okay. So what do you see? The soot volume. So this is comparing diesel. So what is J100 means? Pure, Jatropha. Okay, no mixture, and then 100%, Krenza. Okay, so diesel is producing more soot compared to the biodiesel. Okay, this is plotted versus the crank angle. Okay. So you can see it starts making soot when the ignition occurs. So after ignition, like at 0 degree, you have premixed combustion and the soot is start forming. Okay, and then of course there is oxidation in the later process. Okay. Sorry.
Constant pressure combustion or constant volume combustion, sir?
This is diesel combustion. Well, nothing is constant now because it's a diesel, right? So at 0 degree means piston is at the top dead center. Okay. So ignition, the injection starts at -5 degree from the top dead center, and then ignition occurs. Okay. Yeah, 3-4 degree. So it's very fast. Okay, because it's in the late cycle, so temperature, pressure are very high. It's like a late injection, right? -5 degree. And then you are going up to piston has moved now 20 degree down, 20 or 30 degree down. Yeah, it is almost constant volume when the combustion occurs.
Only if the changes are when crankshaft
Goes very large, right? Yeah, yeah. So you can call it approximately constant. Pressure increases a constant volume. Pressure increases a lot. In the paper they have the pressure plots also, so you can look at that. Okay. So this is for J100 and K100 soot property. This is for J30 and K30. Okay. So now it's a 70% diesel and 30% biodiesel. So now you see all these curves move up. So provides evidence that more soot with biodiesel, or with biodiesel you have less soot.
What kind of conditions to promote oxidation of soot?
Oh, you need oxygen basically. Okay. Oxygen or some other like O, but basically oxygen. Yeah.
From this heat leak, can you comment on the emissions of soot and NOx? For the biodiesel, the diffusion phase that is bigger as compared to the diesel. So we can say that the NOx will be more for biodiesel.
Very good point. Yeah, we have not discussed that part. I don't remember if we did. But you are right. There's diffusion phase is longer, right? So that probably produces more NOx also. Yeah, there is very clear evidence that the biodiesel produce more NOx in engines. They have not pinpointed exactly why. There are some theories, okay, because some also related to the injection, because the injection characteristics are also different for biodiesel. The viscosity is different. Okay. So when it comes out of the injector, some properties are different.
So as you have said that for premixed phase, mainly in that phase, the soot is produced.
Yeah.
If the ignition delay is bigger, then the temperature will be high because all the fuel will burn suddenly.
Yeah.
That will also increase the temperature and NOx will be more.
Oh yeah, yeah. That is known. Yeah.
But we said that soot it depends on the premix.
Yeah.
But if the premix phase, combustion phase is more, then NOx will be more.
Yeah, because the temperatures will be higher. You know. Okay. So yeah, it depends on the injection timing a lot.
It means the NOx also depends on the premix phase.
NOx depends indirectly. If the NOx mainly depends on the temperature. So if you do late cycle injection, it depends. Usually the temperature will be higher. If you do very early injection, temperatures are lower. So then you get this well-known trade-off. Okay. So early injection you will produce more soot, less NOx. Late injection, less soot, more NOx. Okay.
Rather, if you are able to decrease the average temperature at which it is being released a little bit.
Yeah.
Maybe
Yeah. Well, average temperature you can decrease by injection, controlling injection, but also by using EGR. So this low temperature combustion, for example, we go to SCCI, homogeneous charge compression ignition. So the concept is very attractive. It works also very well when you're under low load condition. Okay. But at high load, it's very difficult to control ignition then. Because in diesel engine, okay, the best control is provided from you control the injection timing and you control the ignition. But when you have this homogeneous charge, there are so many ignition spots. Okay, so it's very difficult to control ignition. So they try to make it, if they can make it perfectly homogeneous, you can probably control. But it's not perfectly homogeneous. Yeah. Anyway, we are at the last slide. So you ask any questions, we have like another 10-15 minutes.
So in the heat release rate diagram, top one,
Yeah.
in between 10 to 20 degrees, the heat release rate is high, and the temperature will also be high. It means NOx will be high in that region.
Yeah, that's the diffusion flame region.
Yes. And the soot is also high. So we can see in the bottom diagram the soot from 10 to 20 degree. The soot formation is also high. In the diffusion region.
Yeah, but then it gets oxidized.
Yes, finally it is oxidized.
Yeah.
But in that region 10 to 20 degree it is high in the diffusion burning region.
Yeah, it's being formed, it starts, okay. So you see, this is the premix part where it's formed, but then it keeps forming, okay, because there are those intermediate hydrocarbons, okay, which are producing soot. So now it's like it's being formed and some probably is starting getting consumed, but then here you can say that it's not forming anymore, it's only being oxidized. Okay. So yeah, it starts from almost 0 degree, maybe 2 degree, up to 15 degree or so. Okay, yeah, up to here, and then it starts decreasing.
So we can say finally from these graphs that NOx and particulate matter, both forms at high concentration during the diffusion burning from 10 to 20 degrees.
Yeah, NOx will be formed here also.
And it will be
NOx is not shown here.
but it will be high because
Yeah,
Those
because the temperature highest will be here. Because now the piston is going down, so the temperature actually will be decreasing. So this decrease is also because the temperature is also decreasing. Okay.
So you have lot of temperature versus current kind of temperature. Maybe if you overlap this over the heat rate, right, then
Yeah, they have. I don't know whether I have it in the
it may not
paper.
be necessary that the temperature peak and the heat release rate peak appear in the same.
Oh no, yeah, you're right. Yeah, I don't remember if I have the temperature. Anyway, this is a lot. Any other questions? I can try to see whether there is any temperature. The temperature you can only measure either temperature at some point or some kind of average temperature. So they usually have some data. Yeah, by the way, these experiments were done in this Caterpillar engine. Okay, so it's a one-cylinder engine for experiments. So somebody was asking about NOx. So NOx is higher in diesel, biodiesel. So this is how the NOx is reported. Okay, grams per kilowatt hour. So the data processing directly gives that value. You can see that it is higher, as you were saying also, okay, with biodiesel. But that may be part of the reason, for the higher. Okay. So if you have any questions, we can discuss. Otherwise, we are ready for lunch. Yeah.
Any study for increasing efficiency of the combustion, like using some water vapor or water droplets?
What combustion? Effect of water vapor?
Means just to increase the efficiency of the combustion.
I think there have been studies. And I cannot tell you exactly when it was. There have been studies. You can find injecting water vapor effect on the combustion.
In quantitative term means like suppose 5% or 10% we are injecting, then how much efficiency will increase?
That I cannot give you the correct exact answer. Okay. They have done studies for reducing emissions. Okay. Other part of the research, of course, is fire suppression. They do effect of water droplets on flames or flame on combustion. Okay. But whether it improves efficiency, I don't know.
Nowadays India is working on that so that means combustion temperature will also come down. Now
Yeah.
will be reduced. And
Reduced.
efficiency of means with the 20% injection of the water, efficiency will also increase by 5%. Somewhere it
Yeah, I know there is work because a few years back, maybe 10 years back, we proposed something to DOE with Argonne and myself. We did not get funded. Our proposal was not funded. At that time, we did some literature search for the proposal.
some injection of the metallic powders inside the combustion zone. We studied this model
Metallic,
powders like aluminum or boron.
there is some work. I recently reviewed some paper, I don't know for which journal. They were using some iron particle, iron species, like solid gas species, Fe. So that they found, increases the, combustion intensity. It ignites the mixture earlier.
But it is also a type of pollution. Only for that reason the lead was phased out.
Yeah, the lead was, of course. Yeah, iron, I don't know which iron, it will be iron, some iron oxide will be emitted. Now, vaguely I remember that when you add iron species, so it affects the chemistry and it, through that chemistry it produces more OH, which enhances ignition. No, it involves in the reaction. Yeah, you can say overall effect is catalyst, but yes, involved. So this was from some professor in Korea. Yeah, Korea and China and Japan, of course, there are a lot of combustion research. Any other questions? All right.